All right, so now we've got our different plate tectonic zones here. And so we have this idea of things being driven by convection currents in the asthenosphere. So there is a little information about that here. If you look on this page here, you can see the convection cells in the asthenosphere right over there, right? So if they ask you where the convection currents are, there's your answer. All right, now what's the reason for these convection currents? Density changes. When things get hot, the density goes down and they rise. Okay, we also have things called hot spots, and these are located over mantle plumes. These are single spots that go up like chimney stacks in a way, and as the plate moves over, the volcanoes form above this, and then they move over to the side and they die. So that is our notion of hot spots, and you get a lot of information about hot spots, where they are, on the reference table on our plate tectonic page. So if you're asked where a hotspot is, there's a couple that are interesting that meet up on spreading zones, like one over here and this one pretty close over here. But most of them are kind of isolated away from different spreading zones. Okay, just fixing the camera a little bit there. All right, in a divergent boundary, what we have is that the plates are moving apart. We get new crust there. With the mid-ocean ridge, in the center of the ocean, we get a rift valley and new crust happening in the middle there. And because these things are separating apart, the youngest rock is going to be in the middle. And as we move out, the older rock, the hottest rock, is going to be in the middle. As you move away, it's going to get colder. Then we learned about magnetic striping, how the magnetite gets frozen in its orientation to the magnetic field. And the reason why I put a B over here and a B over here is these are two magnetic stripes. They're in the same direction, and they're also the same age, and that's because they were once in the center here. In the convergent boundary, we have features like volcanoes and trenches and islands, and most of the islands are going to be volcanic, and mountains. And just to give you an idea, everywhere that you have these type of things, you're going to see this pattern here, and you can tell which side is going under and which side is going over by looking at the tabs. And the tabs are always on the overriding plate, the one with the less density. You also see that we have trenches here. We have these little tiny islands along here. Those islands are volcanic islands. So those are our subduction zones or our convergence zones. And we'll find things like mountain ranges as well in places like where India is crashing into Eurasia, right? Okay, this is subduction. The reason why the ocean crust goes under is its greater density. The continental crust is less density goes up. And there's your trench right there, and we'd expect volcanoes to form where this stuff melts. It ends up going upward and creating volcanoes. So then we have our side-to-side motion of the transform boundary. The most famous one is the San Andreas Fault. You expect fault zones, earthquake-prone areas, a side-to-side motion. All right, so now I'm going to start doing some writing in here, kind of caught up with where I think I was in class. So if you have an earthquake, if things are going with earthquakes, a lot of times you're going to need to prepare for that. So you want to have food. You want to have first aid kit with you. Maybe in that first aid kit you have medicine, you have things that you're going to need, like bandages and things for people who get sick. You might want to have fresh water too, because a lot of times the earthquake might cause the water lines to be destroyed or damaged. And you really want to have some type of plan, but I wouldn't put down to make a plan before, because that's kind of common sense. Everybody should know. What are some of the things that you might want to do? For people who live in earthquake zones, you might want to have a plan already done that you've reinforced structures. And that just means that you made sure that those structures can handle things. In a volcano, you want to have an evacuation plan, all right? Because you better get the heck out of there. A tsunami is a giant wave that's going to be caused by an earthquake. That's the reason why we have tsunamis. Not because of the tides, not because of the moon. And so for tsunamis, all the things I did for the earthquake would probably be a good idea too. We might want to add a couple while we're thinking about it. A lot of times you might want to have a radio in line with things. I think flashlight is also a good thing too. Even though people are going to use their phones and stuff like that, phones are going to die out after a while if there's no electricity, so we want to have flashlight, maybe extra batteries. All right, let's go to the next thing. All right, so I know that none of my classes have started this section And so we're going to have to work through this together. So I'm hoping that I'm not going too fast, but here we go. So weathering is the breakdown of rocks. The breakdown. And physical weathering, it's going to cause a change in size and shape. But the object is, the rock is still going to be the same rock. It's just going to be smaller, rounder. And a couple things that were really important with physical weathering, one of the major things in New York State is frost action, where water seeps into cracks, it freezes, and when it freezes, it expands, and that cracks the rock open even more. The climate should be cold and wet, or humid. And we're going to find that that's going to be a lot different than chemical weathering. All right, so let's talk about chemical weathering. Chemical weathering is a change in the chemical nature. So we're really getting something new. Like we can take certain rocks and put them in the presence of oxygen, and we get oxygenation or oxidation and rusting. Sometimes caves are formed when water, which gets a little bit of acidness to it, becomes acidic, runs through, and if it has limestone, it will eat away at the limestone and form caves. Look at what's different. The climate here, instead of cold and wet, has to be warm and wet. All right, so why warm and wet? Well, if some of these things involve dissolving, and if I want to dissolve something like sugar, put it in warm water. I've got to have water to dissolve it, so I want wetness for water. I put it in warm water, it will dissolve faster. So some examples of chemical weathering really you should know about would be the fact that we have calcite reacting.
Hello again. All fourth graders, please return to your projects if you haven't already. Thank you everyone for participating in the 50-50 raffle.
Soil.
We will announce the winner at 7:45. There's still time to get involved if you'd like. The 50-50 is located at the concession stand. Speaking of concessions, thank you all so much for supporting us by buying pizza. It was very popular. We're going to have to do it again next year. At this time, fifth graders, head on out and check out the other projects. Please return to your project by 7:40. Thank you.
All right. They're having the expand here tonight. All right, so what we have here is, for definition, it's going to be a mixture of weathered bedrock and organic remains. That's what makes soil special. It has some organics in there, the remains of living things. Now sometimes, like where we are, we have transported soils. And what that means is that the soil came from somewhere else. It was transported. Glaciers brought much of the materials to our soils, to this area. And when we look at the minerals in our soils here, they don't really match the minerals in the rocks deep down below. So we know that the soil didn't come from the weathered remains of the bedrock that was below here. It's transported by glaciers. So that's usually a factor. And our soils are transported by glaciers. Residual soil means that it formed from the bedrock below, and usually it forms in different layers. So here's just an idea that we would have probably 3 important layers. The topsoil layer contains an organic mixture that's called humus. And you must remember that, I guess. That's a good way to say that, all right? So that is organic remains, along with a really super weathered bedrock. So it's very fine. When we get down in here, we have the subsoil. The thing about the subsoil is usually is mineral rich, because when water runs through the soil, what it does is it brings down the minerals. And remember, water going through the soil, that's called infiltration, right? So in the bottom here, we're going to have some bedrock that is partially weathered. And then down here, we'd have the bedrock itself, the rock layers themselves. So we really have 3 layers of soil and bedrock down below. And what we're going to find is, if this is residual soil, the minerals in here will match the minerals that we have down here. Okay, streams. Discharge is the amount of water transported by a stream, the amount of water. And after rain, you have more water, so what happens is the velocity of the stream increases. So we can make a little chart that says something like this. if we have the velocity or the speed of the stream and the discharge, which is the amount of water, as the amount of water goes up, the velocity of the stream goes up. You see that after a rainstorm, your streams are running really fast. Another thing that's going to increase the velocity of the stream, besides the discharge, is the slope. As the slope increases, velocity is going to increase too. Hey, water's going to go down a steep slope, just like a bicycle would go faster, water's going to flow faster. And as discharge increases, velocity also increases. Okay. Now, when a stream is flowing, it's going to be carrying materials. When it gets to a large body of water, its velocity decreases. And because its velocity decreases, it will start to deposit, and it will undergo what we call deposition. So, rivers that enter a body of water slow down, and there's more deposition when, okay? So we get more deposition when we have more sediment and less velocity. So what a delta is at the end of the river, so here's the river flowing here, the river tends to start to slow down and branch out like this, and because it's slowing down, it's going to drop materials, and we're going to get a almost like triangle-shaped formation that we call the delta. And the most famous delta is the Mississippi Delta, and the Nile Delta. The Mississippi Delta is going to be found down around here, and the Nile Delta is found right around here. Okay, let's move on. Watershed drainage basin is the land area that a river drains. So I'm going to use a little space over here, and what will happen is if we look at an area, we're going to see a lot of streams that bond together, almost like tree branches here. And eventually they end up in one major river. So what we call this area that's being drained by this major river is we call this area right here a watershed area. So our area, our watershed is, we're part of the Hudson watershed. Our streams eventually reach into the Hudson. Let's say this is the Hudson River, and this is our side of the Hudson, and on the west side, we're going to find that we have streams, and there's streams. This whole area is being drained into one big river that flows to the ocean. So what separates one watershed to another is the fact that we have a hill here. We have something where the water has to run down on one side, and then there'd be another watershed over here. Okay? How sediments are carried. Smallest particles are carried in suspension, and that means, suspension means that they don't sink to the bottom. So the smallest ones always remain kind of floating like that. A lot of times those are called colloids. These are particles that don't sink. Some dissolve. And so if we have things like salt, that's just going to dissolve, and it kind of disappears and just flows downstream. So that's called solution when something dissolves. Okay? And the largest are going to roll along the bottom. They're going to kind of bounce along the bottom. And as they bounce along the bottom, they undergo actually a type of physical weathering. Let's go back to physical weathering and add this abrasion. So what abrasion is when you start off with a jagged rock and it starts to roll down the river, the pieces get broken off, and the rock over time becomes more rounded and smaller. So it becomes a rounder rock, a smaller rock, and also a smoother rock. So what's going to happen down here is we're going to have abrasion happening. Okay, this stuff right here, streams moving stuff along, all examples of erosion, which is the movement of sediments or rock fragments. And the driving force of erosion is actually gravity. That's a force, right? The source of the energy for erosion is actually the sun, but the force is gravity because things want to go downhill. Even the fact that we have wind causing erosion has to do with gravity too, because in a way you have air density differences moving one part up and the other moving things downward. All right, so we got wind erosion can cause sand dunes. So let's draw a picture of a sand dune. We'll talk a little bit about how I can tell which way the wind was blowing when the sand dune was formed. This side over here is called the windward side because the wind blows up this way and then comes down over here and it rolls the sand down, and so the sand dune actually starts to move. So this is called the leeward side, and we've heard those words before when we studied climates, right? So the windward side of a sand dune has a gentle slope. Deposition. Deposition is the, I'm going to use the word in here, the depositing of sediments. Okay? And the sediments are usually deposited in a sorted way if we have a stream. So let's just draw another picture that we should be familiar with over here. Here's a part of a pond, or it could be the ocean, and we have a stream flowing into that. And when the stream reaches this, what's going to happen is its velocity is going to decrease. The velocity decreases. And so the largest particles get deposited first. This is a type of sorting, and then the sorting is called horizontal sorting. And so on. So over here we might find pebbles and cobbles, P and C for pebbles and cobbles. The next thing on the list, as far as sizes of sediment, if you forget, is on this page. And this goes on how fast the stream has to go to move particles. I won't really get too much into this. When you use your Barron's book, you're going to go into this a lot more and get some explanations if you need to. But what you're going to have is you're going to have pebbles and cobbles, probably not boulders, but pebbles and cobbles. The next would be your sand, then silt, then clay, and then we go back to those things that never set, that are called colloids, that are going to form out here. So this is likely to form a sandstone over time. This is siltstone, a clay, and then we might get other types of evaporites out here. Now we could do the same thing with the idea that the rounder particles settle faster because there's less air resistance to the denser ones. So we tend to find the rounder, denser, larger particles over here, and we move away over here. Now that's one type of sorting, and that is called horizontal sorting. But every once in a while we can find a type of sorting called vertical sorting. And it usually happens after something like a landslide or a giant flooding event. And in this case, we get a big mixture of sediments all deposited at one time. They're all mixed up, and they're suddenly deposited. This mixture then sorts itself out so that the roundest and largest are at the bottom. And then as you go upward, things become less dense, more flat, and smaller. So this is what's known as vertical sorting after a flood, in which a lot of things are pushed in very quickly. This is the pattern that you get. So in a stream, where does erosion occur? And in a stream, we're likely to find places where the stream bends back and forth. These bends are called meanders. You remember being on a water slide, the water will always go to the outside as it goes down the slide. And that's because the water moves fastest on the outside. So I'm calling this the outside over here, because if I bend my elbow, this is like the outside of my elbow. And so since the water's moving fastest out here, we're going to find that this area is going to have erosion. And here it is again on the outside over here, erosion. So erosion occurs on the outside bend, and deposition is going to occur on the inside bend. See, where there's more erosion, it's actually going to make things deeper. So in a stream, where does erosion occur? It occurs on the outside bend, and also where the water is fastest. All right, so I'm going to zoom in on this because they really show nice pictures over here of what's going on. The depth will then change too. So if I'm looking over here, across here, I'm getting more erosion on the outside. The water velocity is going to be greatest over here, where there's less friction on this area here, but there's not any water flowing at fast velocity. So here we're going to get the greatest velocity right here, not along the side exactly, because there's going to be friction there, there's going to be friction there, so we pick a point in the middle. Over here, this is a straightaway, we get the fastest velocity right in the middle. Over here we have a bend, so we get the fastest velocity on the outside. So over here, I'm just going to put an E for the erosion side here, And then we should also point out that there's going to be a spot where the amount of erosion is equal to the amount of deposition. And that's our equilibrium point right there. That means for every grain that's eroded, a grain is deposited, and there's really no difference. So on this side, while we have erosion, on the inside, we have deposition happening. Okay, so we go back over here to my picture over here. I'm going to put in deposition here, deposition here. Okay. All right, let's go to the next page. In a stream, where does deposition occur? Well, I think we got that. Deposition is going to be occurring on the inside of the bends, of the meanders, inside, and also where it's slower. And so in the diagram, one side is always shallow and the other side is always deep. Just going back to that, you can see that in this picture. Here's the deep side with the erosion, the shallow side has the deposition. Okay, glaciers. When glaciers come through, they take the V-shaped valleys that streams made and turn them into U-shaped valleys. And what I mean by U-shaped is that you would have this happening as the glacier moves down. And sometimes water might pour down through here and give you what are called hanging waterfalls as well along these U-shaped areas. So hanging waterfalls along the U-shaped valleys. Okay, mixed sediments. When the sediments are mixed, we say that they are unsorted. So what happens with these glaciers, I'm going to go over here to this picture, this side over here, is that as the glacier moves down, and it's moving probably to the south, it's carrying along with it stones that it's picked up. And then it reaches a point where the glacier melts right here. It actually starts to melt, and we get a lot of water coming out of that glacier, but this stuff piles up. And we call this glacial moraine. And the glacial moraine is going to be, it's going to be mixed and unsorted. So that's in front of the glacier. Okay, but I do want to point out to you that in this part of the glacier, this is called the outwash plain. And in this part of the glacier, you have streams. And what streams do is they sort out the sediments. So in the outwash plain, things are going to be sorted, but in the moraine, they're going to be unsorted. Okay. Now, one type of structure we have, oh yeah, let me go back to this. Some of the rocks are going to be scratched by the glaciers, and so we are going to find that we might get scratches called striations. And if I see a rock that has scratches in it that are orientated like this, then I know that the glacier moved either this way or that way. So the glacier motion is usually along the striation. And then sometimes we get boulders that just don't match up with what is nearby, and those are called glacial erratics. These are large boulders. There's plenty of them around the Monroe Woodbury area for you to relate to. One type of structure you can get is a drumlin. Drumlin is a big hill that looks a lot like a sand dune. It's made of mixed, unsorted materials. But here's the thing. Sand dunes, we said the wind went up this way to create the sand dune. But in a drumlin, it's almost like going to the playground and going down a slide. You go up this side and you go down this way. So the glacier motion is up the steep side and down. Okay? Now, we also have around here kettle lakes, and they form when we have a glacier in which a block of ice breaks off the glacier and it creates a hole, and here's a hole right here, and then that area just fills up with sediments. Looking back at this, you can see that in front of here we're going to have a lot of material. If a piece of rock or ice broke off, right, it would be left over here, sediments would build up around it, and we get something like this. And then when the ice melts, it leaves behind a depression which fills with water and gives us a kettle lake. Okay, so landscapes. Landscapes are going to be determined by a number of things. First is climate, second is bedrock, and geological structure. So let me talk to you about climate. If you have a hot, humid climate, the features in a landscape tend to be smooth. If it is dry, like in the desert, hot and dry, they tend to be more jagged or more angular is another word we could use for that. Now the other thing about landscape regions is the bedrock itself. What is the bedrock like? And what I mean by that is we have bedrock that could be made of sedimentary rock, and then typically we group metamorphic and igneous rock together. And the sedimentary rocks are going to be part of the landscapes that make up plains and plateaus, while the bedrock in mountains is usually metamorphic or igneous. That's why the Catskill Mountains aren't actually mountains, because they don't contain any metamorphic or igneous rock. And then we have the geological structures. So sometimes what will happen is you might have folding. Folding would be mountain ranges. Or you might have faulting. That's mountain ranges. So those are geological structures. All right? And so here we can see a diagram which gives us three different things here. You see how this is low level. This would be your plain. The rocks are flat. They're horizontal. Horizontal rocks that have been pushed up create a plateau. Those horizontal rocks are your sedimentary rocks. And over here we can see folding happening here. Metamorphic rock. So that's going to be our mountain. Also, the relief is a lot greater. The difference between the highest elevation and the lowest elevation is the greatest in the mountains. Over here there's very little relief, very little difference between high and low. And over here there is a medium difference. Okay, so mountains elevation is high, plateau is medium, plains is low. A bedrock is going to be sedimentary, and then igneous and metamorphic. Okay, sometimes you have to match up drainage patterns with different areas. So what you need to do is you need to look at how the topography is, how the elevations are. And I'm going to leave that up to you going through the Barrett's book and trying different ones and seeing what the answers are as to whether or not you can picture in 3 dimensions how you can go from one thing, which is like a side profile, to a aerial view. All right, half-life. To find out how old certain types of rocks are or certain types of fossil remains are, we use half-life. It's the time it takes for half of an unstable atom to decay into a stable atom. So if you remember, we always get a chart like this where we start off 100%, and as this goes down, the daughter product, what it turns into, goes up. Now, uranium-235, all of these are mentioned on the front page, and after that they don't really give you too much information. But what we would use this for are remains of organic things, living things, within the last 50,000 years. I wouldn't go past that, because after 50,000 years, the amount of carbon-14 becomes so small we really can't detect much of them. Potassium, this would be for your standard rocks around the dinosaur times, and what you do is you check the rocks themselves, and the fossils are about the same age as the rocks that surround them. Uranium, this is for the oldest rock fossils on Earth, oldest rocks, and that's because its half-life is about the age of the Earth, 4.6 billion. And this is for stuff in the outer space where things are really super old. Okay? So over here, this would just be your standard rocks. All right, so how does half-life work? Well, what you do is you start off with the idea that if you have a half-life problem, you probably want to set up a chart that looks something like this. So I'll use carbon-14 as an example, which has a half-life of 5,700 years. I set up a half-life chart. It goes like this: half-life, and then I put my number of years here, and I put my carbon-14 over here, and carbon-14 changes into nitrogen-14. And I start with 0. And at 0, I have 100% carbon-14 and 0 years. So after one half-life has happened,